Yes, that's what I meant. Y equals cosine x. Can you graph? Y equals cosine x over 2 periods over the interval. Negative 2 pi to 2 pi. Can you do that? What's it going to go up to? What's it going to go down to? And where does cosine start? It starts up at 1, 0, 1, and then down, and then up, down, up. Well, I totally missed pi. This one is a down, up, or I put a dot there and didn't even see it.
Wait, you put
Oh.
yeah.
Skip pi over 2, that's what I did. I put it in the wrong spot.
Looks like you need to be doing some more graphing.
I need to do some more graphing. No, you usually don't go left. We don't usually go left very much. All right, so can I ask you another question? I think we asked this one yesterday about the sine graph. Is this cosine graph symmetric about the origin like the sine graph was?
If you flip it over, it's not like the sine graph. If you still
but you can.
Okay, what is this symmetric across?
The y-axis.
The y-axis. Was the sine graph symmetric across the y-axis? It was not. The cosine graph is. If we fold it along the y-axis, it would literally be right on top of each other, wouldn't it? Okay? So we say in this case, cosine is an even function. Somewhere I'm going to write that. Cosine is an even function. What that means is, yesterday with sine, when it was an odd function, if we plugged in x, y, if we plugged in pi over 2, 1, we would get negative pi over 2, negative 1. It was a negative, negative. The opposite ones. But with cosine, if I plug in pi over 2, 0, that's the point right here. Do I get negative pi over 2? Do I get the same answer? Yes. What about pi? If I plug in pi, I get negative 1. If I plug in negative pi, I get the same output. If I plug in 2 pi, I'm going to get a positive 1. If I plug in negative 2 pi, I'm still going to get a positive 1. It's going to be the same output whether we input a negative or if we input a positive. Okay? That is an even function. So whether you put in a positive x or a negative x. I think I wrote this up there yesterday with sine, so I'm going to go ahead and write it up here with cosine. Cosine negative x, plug in a negative value, will output a positive, whatever that's going to be. If you input the negative, it's going to be the same output as if you had plugged in the positive. Does this statement say cosine is always positive? I can't take that away one time when we did this. It does not mean cosine is always positive. So I'm going to do two examples. What's cosine 30? You can plug in your calculator if you've got degree mode. If you're in degree mode, you get a point. Cosine 30, 0.866. Got more decimals. Now plug in cosine negative 30. You get the exact same decimals. They're not even negative. So cosine 30 really equals cosine, actually I should have done that the opposite way. Cosine negative 30. Okay, well that's the first quadrant and the fourth quadrant. What do you know about cosine in the first quadrant and the fourth quadrant? They're both positive. Okay, what about something in the second quadrant? Let's go to the third quadrant first. What's cosine of negative 120? Plug it in. Cosine negative 120. Now plug in cosine positive 120. Do they equal the same exact decimal? That is an even function. Okay, and any function that is symmetric across the y-axis will be that way. That's actually something I went back and was looking through the book from 4.1 that I did not talk about. Sometimes I forget. But it kind of turns into an important thing eventually. But if you do the math, it's going to work out every time. Okay? Even functions, all even functions will have this in common. Whether you plug in the positive or the negative, you'll get the same output. Okay? Alright, so yesterday we talked about reciprocal functions also. What is the reciprocal function for cosine? So 1 over cosine is equal to secant x. So we can take values that we know about cosine and just take the reciprocal of them. So if we start right here at the origin, okay, what is our output? What is cosine of 0 degrees? What it's right there. Cosine 0 degrees, your output is 1. What's the reciprocal of 1? 1. So yesterday, we talked about this, but what if we go to 30 degrees? I think we did it over here. Cosine 30 degrees, 0.86 something, 0.866. Yeah, 0.866025, yada, yada, yada. Now take the reciprocal of that. 1 divided by 0.866. Oh, okay, don't put extra things that aren't supposed to be there. 1.15. Can we go ahead and say What's negative 30 degrees? What's cosecant of negative 30 degrees? Or what's cosine of negative 30 degrees? Do we get the same exact output? Or we get the same exact reciprocal? Yes. So is this dot the same? Do we need to go 45 degrees? What's cosine of 45 degrees? Square root of 2 over 2. Decimals is 0.707. And when I take the reciprocal of that, you simply get the square root of 2, which is 1.4. So we're starting to move up. If I go to negative, so that's pi over 6. Sorry, pi over 4. Negative pi over 4. Is it going to be the same value? We need to keep going. We did 60 degrees yesterday, right? So pi over 3. Pi over 3, 60 degrees. What is cosine of 60 degrees? Pretty sure it's a half, right? We haven't gotten to that. So the reciprocal of a half is 2. We finally got to 2. What about negative 60 degrees? I can't fit this in there. I can. I'm going to. So what's cosine of negative 60 degrees? We're going to have the exact same output. So the reciprocal will be the same. Then we get to pi over 2. It's the next thing on your plate. What's the reciprocal of 0? So 0 over 1. So when we flip it, it's undefined. It's 1 divided by 0. So we will have an asymptote. It cannot touch. What about on the other side? At negative pi over 2, when we have again 0 over 1. Another asymptote. What's happening with these dots, or the cosecant function, not cosecant, the secant function, as it's getting closer to 90 degrees? They get closer and closer to the asymptote. But they never, ever touch it. We did numbers yesterday, the 57, 570, 5,000. Okay? Now, is this everything? Or should we keep going? We've not even gone on the other troughs. Okay, so can I go ahead and jump all the way to pi? Do it. So cosine of pi is negative 1. What's the reciprocal of negative 1? Negative 1. We're still going to be at that same spot. If I want to jump all the way to 3 pi over 2, what's the reciprocal of 0? Undefined. So we're going to have another asymptote. Now, what's going to be happening between this pi over 2 and 3 pi over 2? We've got 1 point. I don't think we have to go through all 6 of these points to get the gist of what's happening. Could we? Of course we could. Okay? But there's a thing about when an original function is decreasing. Does everybody see from this point right here, from pi over 2 to pi, the blue graph is decreasing. Okay? So when we take those numbers and we reciprocate them, you know what's going to be happening? The reciprocal function is going to be increasing to that point. I'm going to draw it this way, but from pi over 2, it's increasing, coming up this line until we get to 1. What happens after pi? The original function is increasing, So the reciprocal function will decrease. Now if we want to jump across 3 pi over 2. Is the blue graph from 3 pi over 2 to 3 pi over 2 to 2 pi, is it still increasing? Yes. So does our reciprocal graph have to start decreasing? So could we start at the top, decreasing, so we get to pi over 2, or 2 pi, and our reciprocal is 1. So this is a pattern. Could we go back this way? Yes. Something we need to notice, and I'm going to write it down in just a second. If your original graph has a 0, your reciprocal graph will have an asymptote at that same point. Okay? Your original graph has a 0. Your reciprocal graph will have an asymptote every time. Does not matter what function it is. If your original graph has a 1 or negative 1, your reciprocal graph will also be at that exact same point. I know. Here we have a 1 as an output. It's going to have the same value. Okay. So the little parabolas in green and the asymptotes are our secant graph. I'm going to go on the other page because this feels like a lot on one page, and it probably is. Okay. So, if your original function has a 0, the reciprocal function, this is something for all math. We're going to talk about this in calculus, and it's going to be not trig functions. There are going to be other functions. The reciprocal function has an asymptote. Trying to think how to say this. If your original function has an output of 1 or negative 1, the reciprocal function will share that point. These are rules for all reciprocal functions. So where there's a 0, which, I probably should also tell you because it's going to happen when we get to tangent. If there's an asymptote in your original function, I mean it was a 1 over 0, your reciprocal function will have a 0. If your original function has an asymptote, I'm going to go ahead and write that up there. I'm going to connect it to the first one. It didn't happen in sine or cosine because they don't have asymptotes. Original function has an asymptote. then reciprocal at that point. Which we won't do tangent before this quarter is over. So these are good rules to know. And it's convenient when we have trig functions and we know they're reciprocals. They actually have functions. They are functions. But when I just give you a regular function, you know, a cubic function or a quadratic or something like that, it has a reciprocal, and you can graph it pretty quickly if you have the original graph. Now, the fun part. Yes, sir.
Can you explain that last one?
If the original function has an asymptote, so in tangent, there's going to be an asymptote in every tangent graph. Okay? So the reciprocal function, so why is there an asymptote? Because we're dividing by 0. So 1 divided by 0. You're going to have an asymptote. But the reciprocal function, when we reciprocate that, we're now, when I flip the 1 divided by 0, it's 0 divided by 1, and that's going to be a 0. So if there's something where there is an asymptote, it will be a 0. That one you're not going to need until after break, until we talk about tangent, really. Yes, ma'am.
So is the output like the highest or lowest?
Yes, that's the y value.
Okay, so if it's like more than 1, the reciprocal function won't be at the point? Like if it like goes higher than 1? You know what I'm saying? Like if the amplitude is like 2 or something?
Oh, no, that's a good question. Thank you. If we do one, because we're going to do one in just a second, what if we have an amplitude that's 2? Okay, so really our output was 1, but then we amplified it to 2. It'll hit at 2. It'll still be that tallest point. Yes. Good question. Okay. All right, so can we graph? Can you graph? Y equals, and we're going to change it up, 2 sine x. And I'm just going to do over one period, unless we want to do the whole thing again. We can. Sometimes it looks cool.
I think it looks.
One period. Because I already drew the line.
You already drew your y and your x. Sine is easier to do over one period because it starts at 0. So I didn't change the period. It's still 2 pi. I really shouldn't. So, eventually, we get to the point of, if you can graph the sine or cosine graph, then graphing its reciprocal function. So now if I ask you to graph y equals 2 cosecant x, you've got the original graph done. Can we graph its reciprocal function? I'm looking at where are the zeros? Where are the zeros in sine x? Here, here, and here. So when I do my reciprocal graph, what happens at those zeros? They become asymptotes. So I'm drawing my dotted line through all of those zeros.
Do we need to label
What do you mean?
Like whenever we.
Oh, the pi over 3, pi over 4, pi over 6 stuff? No.
Okay, so we just.
You still have 0, which I probably should have a 0 there. Pi over 2, pi, 3 pi over 2, and 2 pi. It still has a period, the same as sine does, of 2 pi.
Okay.
And then after 2 pi, it will repeat again. Okay? So now, where we had talked about it was 1 or negative 1, but since we've amplified it, that's going to be an output of 2. We've amplified both of them. So at the point 2, which I have no idea. Another thing we're gonna talk about. Leaving the amplitude at 0, the asymptote at 0, this function is increasing. I use some different vocabulary. So the reciprocal function will be decreasing. So we get to that point. Now we can't touch that line. That line doesn't touch that. Of course not. So after pi over 2, the original function is decreasing. So the reciprocal function will start increasing. So pi over 2. Now, what happens to most? I can't say 100% all, but most functions, after an asymptote, it jumps. So it's going asymptote to positive infinity. On the other side of the asymptote, it's coming from negative infinity. It's what I call jumping the asymptote. You jump from the top all the way to the bottom. Because this graph, again, the original graph with pi, is decreasing, so the reciprocal will be increasing. So we get to that point at negative 2. The original function is increasing from 3 pi over 2 to 2 pi, so the reciprocal graph will be decreasing. Okay. I'm introducing some new vocabulary. Increasing and decreasing functions. We got asymptotes. Now after 2 pi with the same graph, the upward parabola and the downward parabola just repeat again.
Yes.
Yes, it will. It's still a periodic function like sine. Could I do something crazy? No. John's usually the one that says, yes, go for it. Until it's Friday.
Oh yeah, today is Friday.
Today's Friday.
Sounds like a
No,
Did they
it's
sing the
104
song?
days. Oh, I mean,
Oh.
wait, no. No, I mean say days.
What?
Nothing.
I think we're going to graph. Y equals.
Oh yeah.
I'll still be nice. But now I'm not asking for the original graph. But
Can you
guess
still
what?
draw
But
yours
guess
again?
what I'm gonna do? Every single time, I'm gonna draw the original graph.
over one period.
Just one period. Oh, and then you'll see why I like 2 periods when it deals with cosine.
Because there's only.
It's okay. You'll find out. What are you going up to? What are we going down to? Still asking all my same questions, which this one doesn't have in depth. Could I give something with an A, B, C, and D?
No.
No.
Not quite yet.
original graph looks like this. Ish. You know, the first thing I'm going to do for this reciprocal graph, the asymptotes. Find your zeros. Where are the zeros? Zeros means where does the function go through the x-axis? There's only two. For sine, there were three. This one, there's only two. Draw your asymptotes.
That's a pretty cool looking graph.
I know. It looks.
Do you see why I don't like it? To go through just through one period.
Yes, because there's two of them that are just.
You only have half of a parabola there.
That's why.
Okay. So, is it ooh, thank you, Addison. Is secant an even function? Can you flip it across the y-axis
Yes.
and it be the exact same?
Indeed, you can.
Because it would simply do this on the other side.
That's crazy.
Okay. So, original function, decreasing, reciprocal function is increasing. It jumps across the asymptote, so it's decreasing, so its reciprocal function is increasing. It's increasing, so the reciprocal function is decreasing. It jumps across the asymptote. Again. We have increasing, so it has to be decreasing. And I just want to draw the rest of that parabola too. But technically, cosine over one period is that. So secant over one period is just this red function. It is beautiful.
We should do like an art project, but with secret graphs.
Ooh.
They would all look the same. Trigonometry.
I'm afraid to give a piece of paper to anyone. Maybe my front guys right here again. Do
Yeah,
that.
we
one
should
again.
add secant and cosecant to it.
Yeah.
Yeah, and then it's fun when we do tangent. You're like, we need to do tangent posters too.
I bet I won't be shooting.
You bet you won't, but you will. Because I'm gonna ask you questions about tangent at some point in time.
How are we supposed to answer them without a poster?
I will tell you, my calculus class yesterday who had a test turned around and looked at those posters like 4 times. Okay. Did I tell you my other class? There's 11 seniors, and they don't want to pair up, but they've already decided they can't agree on ideas for their poster. So I'm gonna have 11 more posters to go.
Yes. Hang them
So I'm already like
everywhere.
1, 2, 3, 4. I can fit about maybe 3 or 4 in the hallway still. So that's only 8.
Well, there's a Bible verse or whatever.
There is a Bible verse up there, and nobody sees it.
Whatever you do, word.
Whoa, it does. Colossians 3:25.
Is it on the wall?
Yeah.
They painted over it.
Yeah.
This was a first grade classroom.
Why wouldn't they remove it from the wall? Why would they just paint over it?
She was saying,
This was
This
made
is
over
why-
this.
That's so lazy. It's so lazy.
This white is after she.
So was Miss Porter here or was Miss Matthews here?
I don't know. I don't know. Miss McKay.
Actually,
I know
it's
this
3:23.
one.
Oh, we moved on.
They're not named here. It was Miss
Yeah, it's
Porter's
got
room
like the
when she
5
had.
blue.
Yeah.
And then she left and this white came in. I think for just 1 year in this room. Because those 2 years before one, they moved out there. Okay.
Is that not, I know what you can do. You can move these up a little bit, put 1 right here, and then 3 right here.
The issue is the doorknob thing.
Just
Just
one
get rid of
here
that.
And then put 1 here. Yeah, we don't need this.
Yeah. I mean, I have already thought about putting
Wait, Miss
one
Evans.
up here, 1,
But like,
2,
for
for real though.
What
you could
far
do
is
one is like
If
if
you
you
take-
do one over the entrance, so
We
it's
don't
like a
really
big
need this
poster
stuff,
that
do
you
we?
can rip through. Yeah.
Miss Evans, I have an idea.
But I
If
can't
you
fit
take
like
this
3 or
bulletin
4 in.
board down, you could fit like 6 in there.
Or I could just put them on the board.
Just throw 'em away.
You could do that too, because there's a probably gonna do that.
Let's start.
You put it right there too.
It's there.
So I got 2 and 2. Yeah. I could move them closer to the bulletin board and maybe fit on
You
3
can hang
rows.
some up your
outside.
desk.
Yeah. And you guys, they have bet things.
Oh yeah.
Like whoever Kyle comes in and picks his first place, they've already said whoever picks his first place has to go up here and never come down.
Can ours participate in the judging?
We already
Like, or the
won.
ones
Yeah,
that
we already
just
won.
participate in
Yeah.
the judging
Like
of theirs.
be the judge,
No, like
or like be put into that group.
can they? Yeah.
Well, he'll just pick ours again.
Not the ones that didn't play.
That way.
It's okay. The fun thing is they've already planned and thought, what does my husband like, and going with that.
Wait, so they've included you in this bet to where now like you have
We
to
should
keep a poster up there forever.
Yeah.
Are you actually gonna pick?
After they graduate, will they know?
Yeah.
I bet they'll come back
Yeah,
every
they'll
year.
come back just to check it.
And I'm like, well, I'll do it till the end of the year. Hint, hint, they said till the end of the year anyway. Alright, so I have something else for you. Okay, do we need to do another one? No.
Wait, what's next?
If I give you graph 2 minus 1/2 parentheses
No.
x plus 5 over 4.
It's just like you were gonna do it, but we're not.
Okay, I'm sorry, Susie. They're acting crazy. Okay, so could I take the quiz you got back? I may have your quiz somewhere.
So yeah, what y'all learn about
We already have our
We did sign, the original sign in cozy. If you want. I bet Carson took really good notes. So we did sign.
I took really good notes
I have
today.
We already done it.
We did sign, but then we did the reciprocal.
I'm a plate.
Did you not do the reciprocal yesterday? No, you should have signed that. Alright,
Yes, I
So-
warned myself.
on. Back together for just a minute. From your quiz, number 11, when you have y equals 2 plus 3, and I'm going to go ahead and change it. Instead of sine, put cosecant. Okay? What do you do? If
This is the one that I got wrong.
I got it.
This is definitely the one I got wrong.
you're going to graph this exact function as it was a sine function. If you've got your quiz, it's there on it. Well, if you got it correct, just graph that again. If you did not get your number 11,
Boom. Remember.
Yes, I got it, Alex.
so, I went ahead and changed it. We went from -1. Oh, I'm going to have to make this to 5. You know what I'm going to do? I'm going to move my line. And hence, I'm going to move the whole line. Maybe I should write smaller. Is that possible for me to write smaller? I don't know. So sine went from -1 to 5. With our center line, really not good, at 2. Not drawn to scale. Then it started at -pi/2. negative pi over 4 to 0 to pi over 4 to 2 pi over 2. And our sine curve started here, went up, went back down to negative. Oh my goodness, really not long.
That's how mine looks too.
Yeah,
I had one
I think
really
yours
long
was
one.
quite.
Mine looked like that.
Because I had the 5 at the top and the -1 all the way at the bottom.
So that is what your number 11 kind of looked like. So then when I want to find the reciprocal function, where are my zeros? Even though they've been shifted, we're still looking at these zeros. Right there. And when it's at the top, the crest, that's where your parabola is going to go. When it's at the bottom, trough, where your parabola is going to go. I'm not going to ask you to do one quite this intense. Yet. I just realized that you're going to, I did not staple things together. And I did not whole punch things either. If I were to whole punch them, then I would have to take them apart. So, I'm giving you a midterm review. Because we were told to get them this kids by today.
Oh, that's right.
Goodbye. It is not math this Friday. Math is going to be on Tuesday.
Is geometry on Tuesday too?
All math is on the same day.
Okay, so you want to know as long as
Share it.
Apparently Miss Berg read some of our stories. That one.
Oh, I'm sorry. I'm still recording. I gave out a midterm review.